Welcome to the Bristol Robotics Laboratory. I'm Chisan. I'm a microbiologist. Some of you might wonder what a microbiologist is doing in robotics lab. All robots need something in common to operate, no matter what size they are. Can you guess? It's energy. In our team, Bristol BioEnergy Centre, here we make energy using a technology called Microbial Fuel Cells. Microbial Fuel Cell, in short, MFC, is a biological battery that produces electricity using microorganisms. MFCs can be in many different shapes, but all share the same working principles. So, like this typical design, like conventional chemical batteries, MFC has a positive and negative end. We call them anode and cathode. In the anode, we have certain types of microorganisms that are capable of releasing electrons out of their cells. So when we give them food, they digest the food, process the food, and during the process they release the electrons out of their cell if the condition is set for the purpose. And in the MFC we capture that electrons, and the flow of electrons is electrical current. So what can we do with these MFCs? Here are examples, a series of robots called EcoBot. This first generation EcoBot was built nearly 20 years ago in 2002. This one had 8 MFCs here on the top, and this one was the world's first robot that running on sugar that's biologically processed. And then this is a second generation EcoBot. This one had 8 unrefined biomass, such as dead flies and rotten fruit. And these two robots, they sense the light and move towards it when enough electricity was produced. This third generation EcoBot was built 10 years ago in 2010. This one has 48 fuel cells here, so again different shape to the previous ones, and these more power enabled this robot to feed and hydrate itself. So let me explain how this works. Here we have a robot stomach, and this robot attracts flies. So once a fly was captured inside by a chemical, it gets slowly digested in this robot's stomach, and the fly juice will go into all 48 fuel cells. So this is very, very similar to a living creature. So these robots are very special because these robots are not run on chemical batteries. They are like us, they eat food. Would you like to learn more about MFCs and what we do in our lab? You are very lucky today, because usually we have very limited access in the lab to go in, because of the potential contamination, biological contamination. But because it's a virtual, you can get in. My colleague Ivona will show you inside the lab more interesting work we do. Come follow me.
Hello, welcome into the lab. My name is Ivona, and I will tell you a little bit more about what we can do with energy stored in organic waste and how microbial fuel cell can convert it into direct electricity. Let's have a look in here for a moment. This is a microbial fuel cell made of ceramics. This is a ceramic cylinder which holds anode on the outside made of carbon fiber. It's held by the wire which we connect over here, and inside of that microbial fuel cell it's the cathode. Cathode needs oxygen. If we put that microbial fuel cell into a chamber and fill it up with organic waste, and here I've got synthetic urine. So for example, I can add that liquid into the anode. So this is where the microbes will colonize the electrode, converted into electrons. Let's see if we can power a simple motor. This is a windmill toy with just very simple motor inside it, and let's see if one microbial fuel cell can power this windmill. I will just connect. This is the anode, this is the cathode, and it actually operates that motor directly from one single microbial fuel cell fed on waste, on synthetic urine in this case. Let's have a look what other things we can do with this energy. Here I've got something far more sophisticated. This is an EcoBot, exactly the same as Jason presented to you before, made out of 8 microbial fuel cells. These have anodes inside this 3D printed chamber with the anode wire coming out over here. This is the cathode. The cathode needs to breathe oxygen, and we connect it via resistor. However, here those fuel cells are connected together in series, and they charge a small capacitor on board of that EcoBot, and this stored energy is then used for the EcoBot movement. This EcoBot's got 2 photosensors. That means that it detects light and it moves towards it. It performs phototaxis. Therefore, this energy created on board in the microbial fuel cells can be used to move and also to send us information about the environment. For example, it can detect what temperature or humidity is in our lab and send us the information directly, send us the data of that environment that this EcoBot is actually in. So this is the self-sustainable, organic-powered robot. Let's have a look about everyday items. We can power motors, we can power robots. How about our everyday items? How about a phone? Can we charge a mobile phone? And here is a very similar principle. We've got a demonstration that it is urinal, that we can put synthetic urine inside, and behind that urinal, let's have a look. You can see over here there's an array of microbial fuel cell. We call it a stack. So it's a group of microbial fuel cells put together to generate electricity. Then this electricity is stored within those capacitors. If we press the button, then the energy stored in those supercapacitors is being released to charge our mobile phone. It can be also our tablet or everyday devices that we use every day as a storage possibility within the capacitor, which are very similar to batteries. Therefore, all those different devices and applications we can definitely power with microbial fuel cells that process organic waste. And now I'm heading to Jason again, that she will tell you a little bit about this.
So the last piece of work I would like to show you today is will be hopefully very exciting opportunity for you in near future. So far you've seen MFCs, what MFCs can do, powering various applications such as robots and mobile phones. How about what about we have these MFCs in our houses? What if all the building walls were made of MFCs? If so, we can treat our waste, and at the same time that will give us power to use on site. So that's why we designed the fuel cells like this, looking like bricks. And at the moment, we are currently building a website, biodigital interface. So through this interface, when all go functional, you can go to the website and interact with these fuel cells in real time, and your actions, such as feeding microbes or warm heat or cool them, your actions will you will see the microbes respond to your different actions. This website, this work is currently under construction, but when it's ready, we will to it. So if this sounds interesting and you want to have a go, then please follow our BRL Twitter feed, and we hope we will meet you there once again. This is it for today, and now we are able to take some questions from you. Thank you for the visit. Hello again. We moved to this office to have a quiet environment to answer to your questions if you have any.
Yes, happy to take any of your questions or queries you might have about the research and BBiC, and happy to hear from you here on this platform. I think we've got a question. Shall I read it? I have 3 questions. The MFCs, do they have any life?
Life.
Yes.
Yeah.
Or are they rechargeable, as it in just putting fresh biofuel? Would you like to try? Or
Thank you for the question. I can answer the first question. Do they have any life? Yes. The components have its own life. So we cannot have a fuel cell for forever, lasting forever, of course, like all other little gadgets. But as long as we replace these components when they run out, then the bacteria, the community of microorganisms in the fuel cell, they can last. So, for example, in our lab, we have this fuel cells going for over 10 years now, and they're still working fine. We replaced membrane a couple of times during that, but apart from that, the cases still work fine. The microorganisms, the community, not single individual cells, but the community is still working. So, yeah, it's a pretty robust system. And I think Ivona can answer the second question.
yes, thank you very much. Second one was, are they rechargeable, as it just putting fresh biofuel? I think that's exactly right. They are not strictly rechargeable because they are living on microorganisms living on the surface of the electrode, and therefore they will continuously need food, just like us. So if we provide them this fresh biofuel, such as organic waste, they will continue generating electricity. I hope that answers the question. Next one. It appears from what that one motor around 3 to 5 volts being generated.
How are these cells so efficient? Whereas for charging a device like a phone, 3.7 volts is required. Why is a stack required then? Uh, Actually, this motor for of the windmill is low voltage motor running at around 0.25 volts, so 200, 300 millivolts continuously, and that motor will continuously operate under that voltage, and it has to have sufficient current from the microbial fuel cell, which is able to provide. However, the phone is being charged at 3.7 volts, excuse me, and that is, of course, with some help from the supercapacitors, which actually storing that energy. When, of course, the power requirement would be far larger for the mobile phone. So we need to store the energy and then release it to the mobile phone.
Just to add, if I might answer, when we want to power any device application, we need to think about required voltage as well as required current. So these, some devices require high voltage but low current, or vice versa, and that's why the one fuel cell can have about half volt, 0.5 volt, one cell. So if we want to power a device requires 3.5 volts, then we need minimum 7 fuel cells connected together. But then they require different current. So again, we need a stack.
We've got another question. How long do you think an MFC powered robot could stay out in the field because it would be before it would need maintenance? That's a very good question. Thank you very much for that. In terms of maintenance, I think here it would be around materials, what's required. And as Jason already mentioned, what requires maintenance would be the membrane. Microbes that colonize electrodes would not require such replacement. Therefore, the mechanical structure and the design feature probably would be the ones that would need to be maintained. However, that's something, a point for research, for how long we can leave the robot in the environment before it will require a replacement. I think the membranes that were replaced were after 5 years. So I think 5 years would be the approximate time.
And thank you for the nice comment on the brick design. Yeah, we are dreaming of a building house or build a building office with these microbial fuel cell bricks. That would be wonderful. We have a question from Robert. Will the size be reduced in the future? Yes, that's our direction. Our aim. So to increase the power, the one little fuel cell, a small fuel cell, has a limit. So we can. So we need lots of them, and to have many of them, we need to have a stack of many cells. It's like solar cells. The individual cells have a little power, but when we put all together, many of them, then we can have good amount of electricity. But in order to have many of them, we want to reduce the size, so many little fuel cells. And actually, this small fuel cell has bigger power density compared to the bigger size cells. The absolute power output of individual cells might be similar or maybe smaller of small cells compared to the bigger cells. But when you think about the power density, the power output per the volume of each cells, then it's actually higher. So our research direction aim is to achieve the higher power through miniaturization and stacking them together. So yes. Robert asked another question: how small could they be? So in our lab, we have small fuel cells as small as take 1 milliliter or less than 1 milliliter, which is tiny. But we also know other research groups doing micro size MFCs as well. So it can go down quite small.
And I think we've got one question that we didn't manage to answer previous time. And the question is from Kartikeya. Are the MFCs expensive to manufacture?
Yeah, it depends. So in the lab, when people want to test things, you can spend as much as you want. So this very expensive membranes, for example, it can be say about £100 maybe for just one membrane. And electrode, again, if you want to have a really good performance, people use catalysts, and that can be very expensive. However, we are trying to build fuel cells affordable and maybe not that highest performance, but still functional and good enough performance out of materials people can easily get hold of. So, for example, we use ceramic membranes instead of this the ion selective membrane, which is very expensive. And with that, we last 10 years, we have reduced the price of down to 1/10 or even more. But during the same time, we increased power by like 1,000 multitude. So yeah, it depends, and we are working on it to even further reduce the cost and to increase the performance.
Thank you very much. Another question from Claire. Could the MFCs be powered from any organic fuel source? That's a very good question, Claire. And actually, they can. Any organic material has chemical energy locked in, which can be then broken down by microbes and biodegraded. While this process is happening, then within microbial fuel cells, portion of that energy can be recovered as electricity. So any organic matter, which would be compost-like, wastewater, urine, dead leaves, any organic matter that nature itself is biodegrading and recycling in natural ecosystems can be a source of fuel. Yes, that's right, Claire. We could be putting all our food waste to good use, as Claire mentioned, and that's a very good point. We waste so much food, um, and this is actually a perfect energy source. And actually, technologies like that start increasing in our country, as we've seen that food waste can be used by anaerobic digestion, but also we hope that we can develop this technology also with microbial fuel cell to generate electric power. Very good. Thank you. And thank you very much all for joining us today. We hope you enjoyed the tour of our lab and hope to see you again on a similar event like that. And take care.
Thank you.
Thank you.
Bye.
Bye.